Hello everyone, this video is dedicated for the people who missed a lecture on Monday and or Wednesday because of midterms. I know that was almost half the class, so you guys could watch this before going to recitation, and this should hopefully catch you guys up on all the topics that we touched upon in class. It shouldn't be too heavy. I purposely didn't go too in depth with it knowing that this was midterms week, but here we go. So this should give you a good solid foundation before going to recitation so you don't fall behind. Just bring your packet and make sure you watch this video and you should be set with the rest of the class. So let's go over this example problem. So in this system we have a block of mass M1 and a block M1 with a mass of 2.45 kilograms, and then we have another block attached to a pulley system, and block M2 is 5.8 kilograms. All right, and again, these are connected by a massless string, so we're not going to take into any consideration that or any stretching of the string. And they're connected over a pulley in the shape of a solid disc, and the pulley's radius is 0.25 meters, and the pulley also has a mass of 10 kilograms. We could assume that the wedge that these blocks are on is fixed in place, as well as the pulley itself. And the angle that this ramp makes with the floor, as you can see with theta, is a 30-degree angle, and you can see it in the figure below. And also friction will be in place, so this is not a frictionless system like some of our previous problems in Unit 4. And the coefficient of kinetic friction is going to be 0.36, and that's for both blocks. That's the entire ramp. So we have two parts to this problem. We have to first determine the acceleration of the two blocks, and when we were doing the problem in class, we had to enter it into our laptops as a magnitude of acceleration. You can see here, but we'll just work through it on our own. And we also have to determine the tensions in the string on both sides of the pulley. So here, left of the pulley and right of the pulley. So let's examine this logically. We already know off the bat that as I'm looking at this picture, I don't see anything moving. So I can assume that this is at equilibrium, right? This isn't a moving picture. This is a still picture, a still image. So we already know it's at equilibrium. So whatever's left of the pulley, whatever tension that is going to be equal to right of the pulley because it's at equilibrium. Otherwise, it would be heavier on one side or be a stronger, a greater force on one side than the other. And that would mean that this picture is not a picture. That would become a GIF, but this is a picture. So we know that this tension will be the same left and right. That's just, well, that will save us time. If you guys take any exams and you see this, you know that'll save you time as well. But let's just keep that on the side for now. Let's focus on the acceleration of the two blocks. Let's work on this chronologically. So let's make a free body diagram for M1, right? We know the mass. The mass is 2.45 kilograms. What's acting on it? Weight. So the weight is going down. Since it's on a horizontal plane, we have normal force, and we don't need to do any trig to calculate the normal force because it's not an incline like M2. We have friction resisting its motion, but because there is no motion, this is not a GIF, this is an image. Friction is not kinetic, it is actually static, so take note of that. And the formula to find static friction is 1/2 of kinetic friction. So if we pull up our calculator here, we could do 0.36 divided by 2, and that will be 0.18 acting in this direction, right? So K for friction, and we'll just write 0.18 right here on the side, and we're just gonna have it right under the friction so we could keep that. And we just note that this was not kinetic, this is static friction because this is a static image. But as you notice, we are missing one more force. So because friction is acting in this direction, right? Friction, as we know it, is the force that propels things forward. We need something that propels it back. So that's what we're missing. And in this case, because we're assuming that we're going with Newtonian physics, we're missing torque. That's right. We're missing torque. So torque equals inertia, V squared. I'm just going to write that equation there. Normally, I would just put torque and assume you guys know this equation, but because that's new to the unit, I'm just going to keep this here for simplicity's sake. So now we have our free body diagram. We see that all these forces are acting on each other and they're canceling out. So that means that if this is positive x, we can make our x equation, right, for the x-axis, and that would be k, because going in the positive direction, is equal to negative, and then we could just plug in the equation of I v squared, right? Now let's make our y equation. So y is equal to, we have Fn, because we'll just say that right is a positive in the x direction and up is a positive in the y direction. So that's where I'm getting these positive and negative values from. So normal force is equal to negative weight. But actually, let's write that as mg. And now we can plug it solve, right? We can plug it, see what we have. So K, right? What is our static friction? So you have 0.18 equals negative. And what is inertia? Because we can assume that this is on Earth, it will always be gravity squared. That will always be inertia when we're working for physics problems that take place on Earth, which is the majority of these problems. And we have velocity squared, so that would just be 0 squared. So that just means we get 0.18 equals 0. We could subtract 0.18 from both sides. So that cancels this out, and that gives us negative 1.8. Perfect. So let's check. Negative 1.8 here. If we go here, oh, sorry. Well, I actually wrote this decimal wrong. It's negative 0.18. So we have negative 0.18 over here. We go over here. Let's see. Static friction, 0.18. That means this is equal to K. So what is that? That gives us a value of true for B. So we know that this is the acceleration of the two blocks. It is a true statement. Now let's determine the tensions on the string. So we already know, and we can already deduce that, let's say, T1 is equal to T2, right? Because the tensions are the same. And so we have one equation that will be useful for us. But let's actually determine the tension, right? So here, because this is on a not horizontal level plane, we have to use some trick to find the normal force and find the tension. So tension is equal to perpendicular of force normal. So what do we have? T2, we'll say, for the right side, is equal to perpendicular of force normal. And in this case, that'll be mg cos 30. Perfect. Right? So if we plug in, right, let's say we don't even need to subtract this, because let me show you the thought process. I was showing this to the people in class, but if we bring the t over here, the perpendicular over here, these are exactly opposites, so they cancel out. Because if you were to flip this torque upside down, what do you get? You get a t. So that makes them equivalent, but they're on opposite sides of the equation, so they automatically cancel out. So now we just have equals, right? And the torque is gone as well, and the tension is gone. So mg, so actually, let's write the mass of block 2, 5.8, 9.8 for gravity. And then cosine 30. So if we pull up our calculator and we clear, we'll have 5.8 times 9.8 times cosine of, we'll say, 30. As you can see, this properly got inputted in the calculator. So although you can't see the cosine here, it's implied that it's cosine because I just set the new x-axis to be this way. So this is our, y-axis, that's our new positive y. And this is our new positive x, because I don't feel like using trig. And as you can see, that gives us 1,705.2. So let's see. 1705.2. This number is, let's see, positive or negative? It is a positive number, right? So the tension over here is positive, right? And let's see if that checks out. Yep. Why? Because this is in the positive x direction. So if positive here and positive there, that means that this statement is true. And actually, that's for the right of the pulley. But because we have this equation, take note of this, T1 equals T2, then we know that both statements are true. So here you go. This is how you'll solve using tension friction and these different blocks and gravity for this physics problem, assuming that this takes place on Earth, which again we specified in class that all these are implied to be on Earth. So yeah, make sure to study this thoroughly, and hope to see you guys at recitation. Thank you.